Good morning. Good morning. Good morning. How are you doing?
Good.
Good morning.
Okay. Charlie, what's up? What's up? What's up? So Charlie, today we are going to do. Let me admit the rest so that we can start. Mm, Charlie, let's all mute our listening. Let's all mute our sound. Yeah. Let's all mute our sound. Today is my first time using the machine to hold the class. So Charlie, if it doesn't really go, just pardon me. I'll get better. But I know it will be better. Okay. So, I'm coming. So today we are going to do magnetism. Oh, please, those of us with let me mute all of you. Today we are going to do magnetism. We are going to do magnetism. And I know right from JHS, I hope you can all hear me. If you can't hear me, humbly let me know. I know right from, let me off my something. I know right from JHS, we studied a little bit about magnetism. So we know what magnet is about, or we know what a magnet is. When we say a magnet, we know what magnet is. And so today we are going to talk about magnetism as a general topic under elective physics. And after that, we are going to talk about, we are going to look at, I'm coming on. After that, we are going to look at, what do you call it? Ways in which we can, the origination of magnets. I'm filling the form, so I'm on my way, Kakra, and the person is asking a lot of questions. So, sorry. We are going to look at where we got magnets, or the origination of magnets. After looking at the origination of magnets, we will also look at, what do you call it? I'm going to look for test for magnets. How magnets are tested, or how we can be able to ascertain the test for magnets. After looking at that, then we are going to look out for the like poles and the rules that governs magnetization. After looking at the rules that governs magnetization or magnetism, then I think we are also going to look at what do you call it? Ways in which are magnetizing a magnetic material. Before that, we are going to establish the difference between a magnetic material and a non-magnetic material. We are going to look at all these things. Then we are good to go. So that is what we are going to do. Then I think we are going to look out for I'm going to look out for what do you call it? Maybe we might talk, or if we have more time, we might talk on the Earth as a magnet and so on and so forth. Then we are good to go. So good morning once again. If you can hear me, kindly unmute yourself and tell me you can hear me. Okay, you can hear me. Okay. 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 That is good. So let me share the screen. I think my internet is unstable. My internet is messing up. Kindly forgive me. This internet thing. So today we are going to talk about magnets. Now, first of all, we are saying that magnet was originated from a certain mineral or a certain iron ore called lodestone. The magnet was first originated or originates from a certain mineral called or a certain iron called what they call it, lodestone or magnetite. So that is where we had magnets from. Please, I'm coming. That's why we had magnets from. And so the origination of magnets were gotten. Magnets were getting from. We got magnets from, or they were originated from lodestone or magnetite in the form of an iron ore. And when we say iron ore, it's a combination of iron and oxygen. So then we call it iron oxide. And so that is where that was the origination of the originator of magnets. Now,
Sir.
yes,
Sir. Sir.
yes, he said, talk to me. I can't hear you. Hello, hello, hello. Can you hear me? Asa, if you can hear me, kindly talk. Let me see.
Please, recording it. Sir, please, are you recording?
Yes, I'm recording it. I'm recording it.
Hello.
I'm recording it. I'm recording it.
Sir, please, so after will you share it to us?
Of course.
Okay.
So we are saying that I'm hoping the network should be good. We are saying that magnets were originated from, or they were gotten from lodestone or magnetite, and its chemical formula is Fe3O4. Fe3O4, which is an iron ore, and the chemical composition of the iron ore is iron and oxygen. And so the chemical composition of iron ore is iron and oxygen. And so that is where magnets were originated from or were gotten from. And now, one property that makes a magnet so unique is that it has the property of always pointing the same way when freely suspended. So when you freely suspend a magnet, it has the tendency or the property of always pointing the same way. Now, we are able to establish that when a magnet is left freely, it's normally pointing in the direction that when you see the direction, you can see that, okay, this one part is pointing to the north side and one part is pointing to the south part. That is how come we're able to establish that a metal has two poles, which we call the north pole and the south pole, because of how it is. Now, we have some materials we call magnetic materials. we have some materials we call magnetic materials, and magnetic materials are simply materials that can be magnetized. That means materials that can pass through the test of magnetization and get magnetized. It's not all materials that can be magnetized. So those materials that cannot be magnetized are called non-magnetic materials. And a typical example of these materials are what do you call it? Copper and so on. These materials are copper, wood, brass, glass. All these materials are non-magnetic materials. And we have the materials that can be magnetized, or when magnets are passed through them, they get attracted by magnets, and these materials are called magnetic materials. They are attracted by a magnet. Now, from there, we are also going to look at the magnetic poles. We are saying that every magnet is made up of two poles, the north pole and the south pole. And so it is made up of two poles. Made up of two poles. The north pole and the south pole. The north and the south. And the south pole. South poles. So, please. Oh, who is that? The north pole and the south pole. So that is the two poles a magnet is made up of. And this was also established when we realized that when a typical magnet is placed in iron filings. When we say iron filings, these are pieces of ions or broken pieces of iron. So iron filings. When a lodestone was placed in iron filings or was dipped in iron filings, it was realized that, or it was noticed that the iron filings got attracted or got stuck to the sides of, what do you call it, the magnets. So it got attracted to the sides of the magnet. It got attracted to the sides of the magnet. It got attracted to the side. So you realize that if this is the full magnet, let me change the color so that you can see. If this is the size of the magnet, or if you have a magnet, a rectangular magnet, if this is a rectangular magnet, when it was placed in the iron filing, you realize that the iron filings were attracted here. We saw them being attracted here. We saw other parts also being attracted here. And this also made us understand that, okay, every magnet has a point or positions whereby its magnetic influence is felt most or much. And so as a result, we see that the poles are normally the points where the magnetic influence are felt most. And so every magnet or every lodestone is made up of two poles, the north pole and the south pole. Now, and just as I rightly explained in the first presentation, I said that when a magnet is hanged or is suspended freely, it oscillates to and fro for a short time. Now, after oscillating, you know definitely when you hang something, it will oscillate to and fro. That means it will move back and forth. Now, after a little while, it will come, or it will be stabilized, or it will be at equilibrium. Now, when it comes into equilibrium, realize that when a magnet comes into equilibrium, it attains or it assumes two positions, one looking in the north direction and one looking in the south direction. And so we call that the part which was looking in the north direction as the north pole, and we consider the part looking in the south direction as the south pole. Basically, that is it. Now, we have two rules or two laws that governs what we call magnetism. Now, rule number one is that like poles repel, unlike poles attract. Like poles repel, unlike poles attract. So, if, for instance, I have N here, I have maybe yes N pole, and I have maybe yes S pole. Then you are trying to say that if I have, I'm coming. And so this is made up of SS. So now when we have two SS sides, they will repel. That means they won't attract. And most of us who have been using iron, what do you call magnets for a while, you realize that there are sometimes when you turn the positions, when you try joining them, it doesn't join. That means that the poles or the sides of the pole, or the poles or the polarities are similar or alike. That means they have the same poles. That means it's either you are trying to join SS or you are trying to join NN. Now on the other hand, you realize that when they are repelling and you turn it, immediately you turn it, you realize that it gets joined or they get attracted. Then we are saying that unlike poles attract. So under magnetism, it is governed by two rules or two laws. The first law is like poles repel. The second law is unlike poles repel. Sorry, like poles repel, unlike poles attract. So these are the two laws that governs what we call magnetism. Now, the action of one magnet on the other, it performs two actions. Now, the first action, what I said, is a repulsion, which in other words, you see the repel as a repulsion, and the other one is attraction. So it performs two main functions. When one magnet is brought near another magnet, there are two actions that takes place. One is repulsion and one is attraction. The repulsion comes when the poles are alike or are similar or are the same. Attraction comes when the poles are different or unlike poles. Basically, that is it. So these are one of the two actions when one magnet comes into contact with another magnet. Now we have something called test for polarity. Test for polarity. How do we test that this pole is it's been a while I type test for polarity. So how do we know that one side is N and one side is S? Already we've established that when magnets are freely suspended, it assumes that position, the north and the south, Now the side which assumes the north is what we call the north pole. That which assumes the south is what we call the south pole. Now, for instance, I only know that this side, or I only know that this side is north, but I don't know that this side is south. Now, what can be able to help me know that, okay, the magnet I'm bringing close to this, that side is north and the other side is south, is that once I've been able to establish this factor, we call the repulsion rule or the repulsion formula, just from the rules. Because I know this part is N, when I bring one N side to this part and it attracts, then that means automatically I assume that the other side is S. Now, because I already know here, when I bring one side and it is repelling, then I know that the other side is what do you call it? The other side is N2. So that will help me to be able to establish the poles of the new magnet I'm trying to listen. So the first of all, what you are going to do is you are supposed to establish one known fact of the magnet. And so at least if I have one pole here, if I know that here is south, north, then definitely I know that here will be south. If I know here is south, then I know here will be north. Now, how to be able to test? For instance, if I'm bringing this if I'm bringing this unknown magnet to this, I don't know whether here is north, I don't know whether here is south, I don't know whether here is north, whether here is south. So what I'm going to do is, because I've been able to establish that here is north and here is south, when I'm to bring this side to this side and there's repulsion, then definitely I should know that here is north. Now, if I'm to turn it, or when I bring this one closer and it attracts, then definitely I can clearly indicate, or it clearly indicates that here will be south. So that is one test, or test for polarity of a magnet. That is how it is. Now we are going to talk about theory of magnetization, or theory of magnetism. What a magnet is made up of. Now, under the theory of magnets, we are saying that every magnet is made up of molecules. Indirectly, or in other words, we are trying to say that every magnet is made up of fragments of magnets, of smaller magnets. That makes up a big magnet. And so this is to say that this magnet is made up of, when I divide this one, when I divide here, any part I divide, when I divide here and I get this small part, this small part should still have my north and should still have my south. Now, when I combine all of them together, I'm going to get this bigger one, this big lamp. So we are trying to say that every magnet is made up of, this big magnets is made up of fragments or smaller, or molecules of this smaller magnets. And when they are all added, we are going to get this. This means when I break every magnet, I'm still going to get smaller pieces of magnets. And when I get the smaller pieces of magnets, they all act as a full magnet. They all have their knots, they all have their south. That's how it works. And so every magnet or magnet is made up of molecules, smaller molecules. When a magnet is broken into half, the two portions both will still have the distance. So when this magnets, this are broken into half, when this is breaking, we have this in half. So when we further break this one into half, we are still going to get north and south. When we still keep breaking, we are still going to get north and south. So we can't break anymore. So every magnet is made up of this thing, the north and the south. Every magnet is made up of north and south. Then the whole magnet is made up of fragments, or it's made up of molecules of magnets. And so we can now assume that this big side has north and south. Now, when we decide to break it into smaller pieces, then we are still going to get north and south. When we break this one into smaller pieces, we are going to get north and south. So if I'm to draw a line in between this, let me change the color and see. So when I draw a line like this, this smaller piece of magnet still has south and still has north. When I keep breaking them, into smaller pieces, when I break this smaller one will also have north and south. So the more I break, the more they'll still have their north and south. They'll still behave like an user. So the whole of this big magnet is made up of fragments of this smaller magnets, and this we call the molecules of the magnets. Now we are going to talk about something called domain theory. After looking at what a magnet is made up of, we are going to talk about the domain theory. We are trying to say that every magnet is made up of domains. The domain theory. Let me bring it here. The domain theory. This is the spelling of the domain. Domain theory. Now, the domain theory establishes the reason why a magnet can lose its magnetic features or properties, and how a magnet can be magnetized, and so on and so forth. It explains the process it goes through. Now, as we've already established, we are saying that every magnet is made up of fragments or molecules of magnets. Now, when the magnetic materials are unmagnetized, the molecular magnets are mixed up to a point in a random direction. So this smaller, let's represent them by, let me represent this smaller magnet by arrows or by lines. So we have this. So it is made up of this. These are the lines in them. These are all molecules of the magnet, the bigger picture. Now, before this, if this is a magnetic material, for instance, cobalt, maybe this whole thing is cobalt, and cobalt is a magnetic material. Before the cobalt gets magnetized, the molecules in the cobalt are arranged in an uneven position, or are arranged unevenly. So you realize that the lines I'm drawing, they are uneven. They move in they are mixed. They move in different directions. And as a result, because the lines or the molecules in them are not aligned, it makes the material unmagnetized at that point. Now, if you want to magnetize this, then that means we are supposed to make sure that these smaller lines are aligned. And so, for instance, if I'm to draw this one, there's another magnet. You realize that a well-established magnets are aligned. Don't mind my line. So you realize that they are aligned. They move in one direction. So if I was to use an arrow, you realize that they all move in one direction. Sorry, this is not correct, but they are all aligned. So the alignment or the arrangement of the molecules of the material or the magnetic material determines whether the material is magnetized or not. So what you are just trying to say that when they are in this diagram, because they are in a random position, they cancel each other. And as a result, when they cancel each other, we don't have to or we don't expect to get any magnetism or form of magnetism in them. Now, when we look at this one, if you want to magnetize this, then that means you have to make sure that, or you have to put this material into a system that will make sure the molecules in them are aligned at a point. And so the molecules in them, these molecules are arranged, or they are all moving towards a positive or a common goal or a common direction. As a result, when it becomes so magnetizing a piece of iron that consists of 10 its molecules more in line. So if you want to magnetize it, then you have to turn the molecules of these magnets in a good align or in a good shape. I mean, they are supposed to be aligned, and so all of this should move in one distance. They should be straight. They should be arranged orderly. And so when they are arranged orderly, then that means you are trying to say we've been able to achieve or we've been able to magnetize this, and that explains the domain theorem. And so, for instance, when I ask you explain the domain theorem, you are just going to explain. You are first going to ascertain the fact, or you are first going to form the premise that every magnet or every magnetic material is made up of magnetic molecules, or is made up of molecules. Now, when the molecules in these magnetic materials are not are disorganized, then we are seeing that the material is non-magnetized. Now, when we want to get them magnetized, then we are supposed to pass them through a process whereby the molecules in them gets aligned or arranged or are oriented in a good way. It has a good orientation or a good alignment. Now, when they have this good alignment, then we are saying that the material hence has been magnetized. So that is what it means. So when the biomagnet is rolled in pins, more pins cling to the ends and size than the middle. So when I have this biomagnet, just I've already explained, when you place it into a pin, like the seamstress pins, the what do you call it? I know that these people also uses it. The electricians, they also use it to keep their screws. You realize that when they listen, the screws will be attached to this ends, which is the poles, and that establishes that they are what do you call it? They are and you even sometimes you realize that after taking off the pins, when you bring two pins together, they attract because the pins get magnetized when they are attracted to when they were attracted to what they call the main magnet itself. Now we are going to talk about magnetizing a magnetic material. Having been able to establish the meaning of the domain theorem, we are now going to talk about magnetizing a magnetic substance. Now, when we say magnetization, then we are just trying to say that it's a process whereby we make a magnetic material magnetized, or we pass a magnet through a magnetic material. In other words, I'm just trying to say that if I have a magnetic material like cobalt, now cobalt before getting magnetized had no magnetism or signs of magnetism in it. Now we pass it through a process that the cobalt can live on its own as a magnet. Then when we are able to establish that fact, then we are saying that okay, the cobalt or the pin has been magnetized. Now the pin moves or lives alone as a magnet. It's able to attract or repel another pin. Then we are saying that the pin has been magnetized. That process is what we call the magnetization. And we are going to talk about 4 or 5 methods in which a magnetic material can be magnetized. Now, method 1, we are going to talk about the electrical method, and it's so far the best or expedient method to magnetize a material. Now, with the what do you call it? With the electrical method, a piece of nail or a piece of material which is going to be magnetized is passed through what do you call it? A solenoid. Now, when we say a solenoid, so for instance, if I have a nail here, this is a nail. In 10 minutes time, let this one go, but we start again. If I have a nail here, let me look at the color. So if I have a nail here, for instance, this is my nail, and this is the nail. We want to make sure we get this nail magnetized. Now we are saying that the nail will be passed through constant or a solenoid. Now when we say a solenoid, I'm coming. When we say a solenoid, it's a cord wire, and so this is a wire. This is the wire. Now, when it is passed through this wire, then the wire is connected to, what do you call it? The wire is connected to a resistor, definitely, just to oppose the flow of current. So it will be, the wire will be connected to a resistor. And so, you know, this is how a resistor looks like, a rheostat. Now, so the rheostat controls, what do you call it? The flow of the current. Then it is connected to a DC. When we say a DC, direct current, I explain what a direct current is. The current moves in only one direction. So it's like a battery. It's connected to a DC, and definitely we connect it to our switch. So this becomes our switch. Then we are able to get our full diagram. So this is the solenoid. This is the solenoid or the wire, the coil of wire. I was supposed to use a different color. And this is the wire. This is a part of the solenoid, you know. And so the wire which serves as a conductor, and it is connected to the DC source. So it is connected to the DC source. So it's the duty of this, and it is plugged. So this one, this, as the current passes through the wires, a magnetic influence or a magnetic field is set around this here, around the coil here, Now, when that magnetic influence is set around the coil here, it automatically gets this nail magnetized. It automatically gets this nail magnetized. So that is it. And depending on the flow of the current, the polarity of the magnetized specimen depends on the direction of the current. So the flow depends, or the polarity of this magnet, the new magnet you are forming, depends on, what do you call it, the direction of the flow of the current. So it's dependent on that. If the current at one end flows in a clockwise direction, on looking into the solenoid, the pole at that end is the south pole. So if the flow of current at one end is flowing in a clockwise direction, and that means that side becomes north. Now, if the current at the other end is flowing in an anti-clockwise or anti-clockwise direction, and that means that part becomes north. That's what it means, and vice versa. That's what it means. And so, and this is one of the most efficient way we can get a magnetic material magnetized. And this one normally stays, or it makes the distance. After the ejection of the magnetic material or the nail, it takes a longer time before it loses its magnetic property. It takes a longer time before it loses its magnetic property, and that is it. And this is so far the most efficient, or this one prolongs the magnetic material or the magnetic feature of the this thing. So afterwards, when we get it magnetized, it is supposed now to behave like a magnet. And so that means after taking away this, when I bring another nail close to this, it's supposed to attract or it's supposed to repel. And that means that it has gained or it has been magnetized. That's basically what it means. Now, from there, we are going to look at another one we call the stroking method. Now, under the stroking method, we have the two types of stroking method. We have the single stroke or the single touch method. And so this one, let me just write the distance. Let me push this one forward. And so now I can confidently write that this one is magnetization by electrical method. Now we can also establish one which we call the magnetization. So this one to be magnetization by stroking. Stroking. Now, the stroking, I'm going to consider the single touch method. And we are going to talk about the double touch method. Now let's consider the single touch method. Please, we have about 4 minutes, so let's use the distance. So the double touch method or the single touch method. Now with the single touch method, what we are going to do is, for instance, let's use the same nail. If I have a nail like this, and I want to get the nail magnetized, what I'm going to do is, I'm going to use a magnet. I'm going to stroke or I'm going to strike. If you can still use a stroke. I'm going to stroke a magnet on this, on the axis or on the lines of this magnet. So this magnet gets magnetized, and the more I stroke, the more this material gets magnetized. So for instance, if this is so if this is a magnet, it has maybe north pole, south pole. Now the more I strike or I stroke from this side to this side, I strike or I stroke from this side to this side, from this side to this side, I get this magnetic material. For instance, this is nail. I get this magnetic material magnetized by this method, and this method is what we call the stroking method. So in the single touch, the material is stroked from one end to the other end several times in the same direction. And so this one is stroked from one end to another in the same direction with one pole of the magnet. And so if here is not, I'm going to stroke this material from here to here in the same direction with one pole. And this pulls the opposite poles, the opposite poles of the molecular magnets in one direction and leaves them pointing one way. And so one disadvantage you realize is that because you are going to stroke with one side, it makes one side gain more magnetivity or gain more polarity than the other side. So as a result, we had to find new ways we can be able to make sure they are all at the same tangent, or they are all at equilibrium in terms of polarity. And so we introduce the double touch system. Now with the double touch system, what we are going to do is that we introduce another magnet. And so now we strike them inward. And so if I have this, and so for instance, if here is north, here will be south. And so this strikes, or I strike this one, or I stroke from here to this point. This one also stroke from here to this point in the same direction, from here to this point. This one strokes through from here to this point. And as a result, because you are using two magnets, you realize that after the whole process, after doing it several times, we are going to establish that they all have both good polarities, and that solves what we call the deficiency in the first one, the single stroke this thing, what do you call it, method. That solves the distance. So you realize that with a single stroke, the more you strike from here to here, you realize that here, if here is north, then here will become north, then here will become south. Now in the double, what do you call it, the double stroke system, with a double stroking system, you can strike from here to here, can be able to strike from here to here. Now if here is north and here is south, when I keep striking from here to here, I'm going to get an exchange polarity. So when I keep striking from here to here, and I keep also striking from here, for instance, if here is north, then I'm going to get the polarity of this one here to be south. I'm going to get here to be south, and I'm going to also get here to be north. And this side, I'm going to get this side. Let's say if here is north and here is south, then I'm also going to get. I'm going to get here to be north. So this is how this system also works. So for instance, when